Good morning/afternoon, everyone. Today, I am excited to present our paper titled MAC-Lookup, Multi-Axis Conditional Lookup Model for Underwater Image Enhancement, which has been accepted to IEEE SMC 2025. This work is a collaborative effort by researchers from Guangdong University of Technology, Huizhou University, and other institutions. Our project addresses the challenging problem of enhancing underwater images, which are often degraded by factors like light absorption, turbidity, and bubbles. We propose a novel two-stage framework that significantly improves color accuracy, contrast, and structural clarity. A demo and a source code are available on GitHub, which you can access via the link shown here. Underwater image enhancement is crucial for marine exploration, robotics, and ecological monitoring. However, underwater environments introduce unique challenges such as color distortion, reduced contrast, and uneven illumination. Traditional methods often rely on physical priors or handcrafted features, which lack robustness in real-world conditions. Deep learning methods, while promising, suffer from the scarcity of high-quality paired training data. Our goal is to develop a method that effectively restores natural colors and details without over-enhancing or introducing artifacts. Existing methods face several limitations. Traditional approaches often lead to oversaturation or unnatural color transitions. Learning-based methods require large paired datasets, which are hard to acquire in underwater settings. Many models fail to handle local variations in lighting and turbidity. Our motivation is to overcome these issues by designing a model that integrates both global color correction and local detail enhancement in an efficient and scalable manner. For above issues, we propose the model called MAC-Lookup. The whole model framework is shown in the image. It is clear to know that the MAC-Lookup consists of two main components: Conditional 3D Lookup Table Color Correction, CLTCC, and Multi-Axis Adaptive Enhancement, MAAE. The CLTCC, Conditional 3D Lookup Table Color Correction. This module performs initial color correction using a learned 3D LUT, which efficiently maps degraded colors to enhanced ones with linear complexity. As for MAAE, Multi-Axis Adaptive Enhancement, this module utilizes a multi-axis design to balance local, CONV, and global, MLP, modules, enhancing detail restoration and natural color transitions. The cross-gating block, CGB, improves encoder-decoder interaction for better global consistency. Post-CLTCC, multi-stage MAAE further refines image quality using supervised attention blocks, SAM, for feature extraction across stages. This design surpasses current best results and ensures both color fidelity and structural clarity without extensive pre-training. Let's now look at the numbers that back up these visual results in the table. We evaluated our model on 3 standard datasets using PSNR, SSIM, and LPIPS metrics. The MAC-Lookup outperforms other methods on the UIEB dataset. It matches semi-UIR in PSNR and TUDA in SSIM and LPIPS, proving effective in solving color issues and preventing over-enhancement. MAC-Lookup's MAAE component enhances interactions in global and local branches, improving predictions. On the UIEB dataset, 90 test images, MAC-Lookup achieved a PSNR of 23.84, an SSIM of 0.923, and an LPIP score of 0.103. This outperforms the second-best method, semi-UIR, by 0.20 in PSNR and significantly improves on TUDA's LPIPs. On the EUVP dataset, 200 test images, we scored a PSNR of 26.85, SSIM of 0.891, and LPIPs of 0.139. This represents a gain of 0.27 in PSNR and 0.036 in SSIM over the previous best method, IACC. Most impressively, on the large LSUI dataset, 200 test images, MAC-Lookup achieved a PSNR of 27.78, SSIM of 0.931, and a very low LPIPs of 0.099. This is a substantial improvement, beating TUDA by 2.26 in PSNR and 0.055 in LPIPs. As shown in visual comparisons, traditional methods cause color distortions. See-through and PUGAN inadequately improve visibility, while FNIEGAN, IACC, and U-transformer fail to enhance contrast and face issues like local darkness and over or under enhancement. As shown in visual comparisons, see-through, Bayesian Rednex, TUDA, ICSP, and Pugin struggle with color restoration, making yellow areas appear gray. IACC and U-transformer restore yellow tones but fail with contrast, while FNIEGAN and ROP improve color partially but have contrast issues like local darkness or uneven enhancement. In the image, see-through significantly distorts color in hazy images too. ICSP and IACC do not effectively remove blur, reducing visibility enhancement. ROP introduces local darkness, and other methods fail to improve contrast, facing issues like darkness and improper enhancement. In summary, our method effectively removes unnatural colors, improves visibility, and prevents over or under enhancement. According to former experiment table, it achieves the highest PSNR and SSIM, and the lowest LPIPS values, indicating superior contrast, brightness, and texture detail enhancement for natural colors and high visibility. To validate the contribution of each component, we conducted thorough ablation studies. We measured the average performance across all three datasets. First, when we removed the MAAE module, without MAAE, the performance dropped to a PSNR of 25.74, SSIM of 0.9123, and LPIPS of 0.1229. This shows that without MAAE, the model loses its ability to adaptively enhance details and maintain contrast. Conversely, when we removed the CLTCC module, without CLTCC, the results were significantly worse, PSNR plummeted to 18.20, SSIM to 0.7793, and LPIPS increased to 0.3076. This confirms that CLTCC is absolutely crucial for establishing a strong foundational color correction. Finally, our full MAC-Lookup model achieved the best results, a PSNR of 26.79, SSIM of 0.9147, and LPIPS of 0.1159. The numbers clearly show that both modules are essential and synergistic for optimal performance. In summary, our key contributions are: we propose MAC-Lookup, a novel two-stage framework for underwater image enhancement. We introduce CLTCC, the first conditional 3D LUT-based color correction method for UIE. We design MAAE, a multi-axis enhancement module that effectively combines local and global cues. We achieve state-of-the-art results on 3 benchmark datasets, with clear quantitative and qualitative improvements, and release an open-source implementation to facilitate further research. Thank you for your attention. We welcome any questions you may have.